In this video, we're going to look at one more problem that involves BigO. So the problem here is I need to show you, I need to show, I need to show that x squared plus 1 over x plus 1 is BigO, BigO of x. Okay, now if you've been watching my videos, the first and the second video, think of think of this think of this function over here as a function which is f of x. Okay, this is something that happens to be the actual performance of your algorithm. So when you feed it some problem size x, when you feed it some problem size x as input, so this is your input, the problem size. You're measuring you're measuring f of x, and f of x over here could be the number of steps of your algorithm. It could be the number of steps. It could be the time taken. Maybe it's the time taken for the algorithm to execute, or it could be the memory consumption. It is something that you're actually measuring, and the function over here is and the question over here is that I need to show x squared plus 1 over x plus 1 is bigger of x. So first thing, again, to kind of give you an intuition, what this question really means is that if this statement in orange is actually true, then there must exist some c and some k that is going to make this inequality true. Okay, so for some x being greater than k, right, where c and k are positive constants, this entire expression, this entire inequality is going to be true when 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 x squared plus 1 over x plus 1 is bigger of x. So first what we'll do is we'll run Wolfram Alpha to kind of get a graphical to see what is the how do these graph look like when I plot them, get an intuition before kind of jumping into the calculus interpretation of this expression. So let me just turn on Wolfram Alpha here, and if I get Wolfram Alpha running, which is over here, let's first plot x squared plus 1 over x plus 1. So I'm going to plot x squared plus 1 over x plus 1, and then what I'm going to do is I'm also going to plot the function g of x, which is x, and plot x, and we want this between 0 and let's say 10 for now. So let's plot these functions, and I can see in here, let's just make the domain a little bit smaller. Let's make it 0 and 5. And what I can notice is this is my function. This is my function in red is g of x. This is my function g of x. And over here, x squared plus 1 over x plus 1 in blue is the actual function f of x. And the question here is f of x bigger of g of x? And I can see that the statement is actually true because g of x, the function g of x over here, which is in red, does happen to be an upper bound. It does happen to be an upper bound after you cross this k, whatever that k is, for all x that happens to be greater than k, for all these x's here, I can see that the function c times g of x, where c over here happens to be 1 times g of x, which is this function over here, is actually greater than the function in blue. And the function in blue over here is f of x. Okay, so the statement in orange is actually true. Let's go back to our statement in orange, and let's minimize this, and and I can see that this is absolutely okay. Now what I'm going to do is I'm just going to rewrite this. I'm just going to rewrite this again over here. So let's rewrite this as x squared plus 1 over x plus 1 is less than or equal to c times x. Now let's divide both the sides on this inequality with x. That gives you x squared plus 1 over x plus 1 over x. And let's see. Now I know x over here is a positive value, and because it's a positive value, I can make sure that these inequalities are completely preserved as I perform this division. X cannot be negative. And this means that what I have over here is x squared plus 1 over x squared plus x is less than or equal to c. Now, with asymptotic analysis, as we're looking at asymptotic analysis, as we are learning asymptotic analysis, one of the questions that we're trying to address here is, what is the performance of your algorithm as the problem size becomes larger? The problem size over here is x. The problem size over here is x. So what happens? What happens as x goes towards infinity? Meaning, what happens to this limit? What happens to this limit as x tends towards infinity? Now, if I look at this expression and I plug in x as infinity, what I see on the numerator is infinity squared plus 1, which is infinity, over infinity squared plus infinity. I'm just plugging in infinity for x here. I get infinity squared plus infinity, which is infinity. And the moment you have an expression which happens to be infinity over infinity, or if your expression happens to be 0 over 0, which is an indeterminate form, I can use the L'Hopital's rule, which is the rule that says limit of x going to infinity of some function f of x over g of x. This is equal to limit of x going to infinity of f prime of x over g prime of x. Okay, so instead of using this expression over here, I can simply use this expression over here where I take the limit of x tends to infinity, and I take the first derivative of the numerator. I take the first derivative of the denominator, and then I plug in x going towards infinity to solve what the limit value should be. Okay, so let's do that. Let's take the first derivative here. So when I take the first derivative of this box in yellow by applying the L'Hopital's rule, I can see that the numerator becomes 2x, the denominator becomes 2x plus 1. Okay, and again, when I plug in my x as infinity, I still have this form of infinity over infinity, and to solve for the limit of this expression, I can apply the L'Hopital's rule again to give you 2 over 2, which is equal to 1. So the limit of this as x goes towards infinity, this entire expression over here is going to be equal to 1. Let's just try this out. Just to make sure that this is true. So I'm going to open up Wolfram Alpha again, and the tools of doing this. First, let's just plot this, which is x squared plus 1 over x squared plus x. X squared plus 1 over x squared plus x, and I will plot this for large values of x, where x goes between 0 and less than 1000 for time being. Okay, so, and I don't need the other values. Let's just plot this again. And what I can see here is that that this expression, the function in blue over here, which is x squared plus 1 over x squared plus x, as x over here, which is my denominator, as x goes towards infinity, this function over here gets closer and closer to 1. Right? It gets closer and closer to 1. So the limit of this function over here, as x goes towards infinity, is going to be equal to 1. Okay, so what does that mean here? It means that the limit does exist. The limit does exist for this function, and the limit over here is basically some constant 1. Okay, the other way to check this is I can just tell Wolfram Alpha, give me the limit for this function, and as you can see here, that as x goes towards infinity, the entire term, the entire limit for this expression is going to be equal to 1. Okay, so coming back to my problem here. back to my problem. I can see that the limit over here is equal to 1, which means that if I choose any c, such that it happens to be greater or equal to 1, right? I can choose any c that happens to be greater or equal to 1, and that will satisfy this entire inequality. The entire inequality will be satisfied. But c must be greater or equal to 1. I cannot choose any c that happens to be less than 1. So let's try this. Let's come back to my plot here. And what I'll do is I will come back. Let's plot the original function, which was x plus 1, not the denominator. So I'm just going to plot right here. I'm just going to plot x squared plus 1 over x plus 1. This is x squared plus 1 over x plus 1. I'm also going to plot the function g of x, which is an x here, and these are for values between 0 and 100. Now what I can see over here is that in this case when I have x being equal to 1, both the blue and the red curve are completely equal to each other, very equal to each other. Okay, and this is fine because the red curve, which is on g of x, is perfectly an upper bound on this blue curve. Okay, and this is great, and this will completely hold true for any c that happens to be 1 or greater than 1. So if I try this, let's say with a value of 2x. If I make it 2x, the red curve will still be an upper bound, on this blue curve here. I'm just ensuring that this inequality, I'm always making sure that this limit that involves the inequality is preserved. Okay, so if I choose a value of 1 or any value of c greater than 1, this inequality will be preserved, meaning that the function g of x will be an upper bound on the function f of x. However, if I choose a value of c that happens to be less than 1, meaning something like this, let's make it 0.5. And now if I plot this, I can see that the red curve will no longer be an upper bound. This red curve is no longer an upper bound, and it's not an upper bound because my inequality over here, which says that c must be greater or equal to 1, has been violated. And the moment this gets violated over here, you will have a function g of x times some constant c not being an upper bound on the blue curve. Okay, so this is kind of the calculus interpretation of the question that we looked at in this video.